talk about how to generate an unsymmetrical product where we have a different donor aldehyde and an acceptor aldehyde. I'm just going to choose, not randomly at all,
perhaps something that will show up on the quiz.
a product that I was trying to make in my graduate or my postdoctoral work.
Oh, never mind.
Which is 3' and 5' dimethoxy ketone. Which actually might show up in your group projects at the end of the semester. So the new bond we want to make is that carbon-carbon bond between the carbonyl group and the alcohol, and the aldehydes that would be coupled from that if you look backwards. Benzaldehyde on one side, and 3,5-dimethoxy benzaldehyde on the other side. So the first thing we need to decide is which one of these is the donor and which one is the acceptor. And then we have to figure out how to make the donor into a donor. The acceptor is no problem, right? Both of these aldehydes have a partially positive carbon from the carbonyls because they both have that minor resonance structure with a single bond to oxygen and a positive charge on carbon. So the acceptor doesn't require modification. But the donor needs to be that acyl anion, so we're going to have to figure out how to generate an acyl anion equivalent. So who's the donor and who's the acceptor? So which one still has a double bond? Because that's the donor.
Wait, say that again?
Which carbonyl is still a carbonyl group? That's the donor, right? The acceptor is going to be turned into the alcohol because we're going to do nucleophilic.
Oh, you're saying in the product.
Right.
So that means benzaldehyde is the donor?
So this one is the one we want to use as a donor. This is the one we want to use as the acceptor, so that we can make the new carbon-carbon bond here. We can do a nucleophilic acyl addition across here. What we need to do is a nucleophilic acyl addition of this impossible compound we can't actually make. Right? We want that acyl anion. You can't make that acyl anion by deprotonating benzaldehyde because that doesn't work. So what can we convert benzaldehyde into that will generate something that isn't that can be converted back into that when we're done. And the key, again, is going to be to place that hydrogen in between two electronegative elements. So on a carbon that's in between two electronegative elements in a ring, so we can stabilize it. And to do that, generate diketones. So this is a thioacetal formation. Which we saw way back in chapter 17, where we take 1,3-propane dithiol and a Lewis acid. And at the time, I think I told you that this hydrogen is acidic. Not very acidic, not pKa of 17 to 19, right? Not as acidic as the hydrogen found in thiazolium salt, but acidic enough to be removed by a very strong base. And the usual base is lithium. So we're going to take our lithium and take that hydrogen off, generate a butane, and an alpha lithium. But because that negative charge is between the two sulfurs, it's a lot less basic than your standard alpha lithium, which means we can get it as a nucleophile. Just as we had with the thiazolium salt, that lone pair is in an sp3 hybrid orbital. It's not in a pi orbital. So we can't actually draw resonance structures that puts a negative charge on the sulfur. But the sulfurs can withdraw electrons inductively and stabilize the negative charge on that carbon. And you'll notice that in this particular case, because the aldehyde we're using as a donor is aromatic, we also have the ability to resonate that through the grid. So it's in a benzylic position, and that makes it even more acidic. So it works particularly well when the donor aldehyde is attached to an aromatic ring. This alpha lithium can now do all the same things any other alpha lithium reagent could do, including add to a carbonyl group. So we can add that to the carbonyl group with the acceptor aldehyde. Carbon-carbon bond. Salt. So that's kind of a standard nucleophilic attack. And it will sit there as the lithium salt of the alkoxide. So we work that up with some aqueous acid. Where it will get protonated. So that's a nucleophilic acyl addition. Step 1 is a nucleophilic attack. Step 2 is to protonate the alkoxide. That's not the product, though. That still has the dithiane ingredient in it. So what do we have to do? We chop that guy back off to generate the carbon. So now it's done its donating. I'm going to take that off. So we're hiding the fact that this is an aldehyde hydrogen. N-butyl lithium wouldn't take off an aldehyde hydrogen. But it doesn't know that's an aldehyde hydrogen because it's attached to that dithiane that you said. So this hydrogen is basically faking it. It's saying to butyllithium, I'm not an aldehyde hydrogen. Look, there's no carbonyl next to me. You can take me off and make an anion. And then at the end it says, ha, just kidding, no, it's an aldehyde hydrogen all along. Fooled you. So how do we remove the dithiane group? What's the reagent for that? Go back to your chapter 17 memory. Because that dithiane group can actually be converted to lots of things. You can take that back off to regenerate the aldehyde. And you may also remember that it's possible to convert the dithiane group to a CH2. So we can convert it to the anion, we can convert it to the aldehyde, we can convert it to the CH2. And I'm hoping you remember the reagents that go into these two arrows. Chapter 17. What was hopeful? You're going to remember things.
I want to say it's something to do with zinc, but that sounds wrong.
Zinc is the other way to put it on.
Oh.
So if instead of using BF3, you use zinc chloride.
Just kidding. Scratch that.
So that's Lewis acid.
I know we break the alcohol ones with
Yep.
H3O plus.
Yep, but the dithiane is much more stable to aqueous acid than the regular acetal. So we don't usually remove it with aqueous acid. If you crush it with enough aqueous acid, it will come off. And in this case, the rest of the molecule is stable, so you probably could crush it, but that's not the normal way to remove it. We normally exploit the fact that the other name for sulfur, right, the other name for ethyl is called a mercaptan,
So my guess would be mercury.
and that's short for mercury capturer. So the normal group that removes the dithiane is some kind of mercury salt, and maybe calcium carbonate in there as well, but it's a mercury 2 salt that takes that off, because mercury and sulfur have a special affinity for each other. When you spill mercury liquid on the floor, you can dust it with sulfur, and it will react to form mercury sulfide. Mercury sulfide is one of the least soluble sulfides there is, so you can get your mercury cleaned up that way. So that's how we get it back off. We use pure chloride, mercury 2 chloride. Remember these reagents, how do we desulfurize?
Could you do that, or H2 and NH2, is that the same as?
H2 and NH2 would go directly. Right, that's Wolf-Kishner? In base.
So you're saying.
You wouldn't need the dithiane at all, right? You go directly from the aldehyde to the.
Oh, you're saying starting from the dithiane.
Yeah, how do we desulfurize to make dexamine? So the Wolf-Kishner reduction would certainly be an effective way of converting the aldehyde to the CH2 group. But in this case, we made the dithiane. Now we want to desulfurize it to make the CH2 group. And the answer is green nickel and hydrogen gas. So radionickel desulfurization is the way to convert the dithiane. Right? There are 3 different ways of converting a carbonyl group directly to a CH2 group. We've studied 2 of them, the Wolf-Kishner, which is in basic solution, and radionickel, which is neutral, hydrogen gas. And we'll talk about the other one, which is the Clemens reduction when we get into the aromatics. So it's a multiple step procedure where we take our donor aldehyde and make the dithiane out of it, deprotonate that with alkyl lithium, add that to our acceptor aldehyde, and then remove the dithiane using mercury chloride. Once we have that alkyl lithium, that needs to replace, so we put it back. It can do other reactions that alkyl lithium do, or organometallics. So what can you add an alkyl lithium to generate a ketone instead of an alcohol? So we took alkylithiums and we added them to, not carboxylic acid, right? If you add that, that's a really strong base. All it's going to do is deprotonate the carboxylic acid. But we could add it to various acyl derivatives, right? So we did this, right? We took a Grignard, and you add that Grignard reagent to
Oh, yeah.
a carbonyl group like this, and either an ester or an acid chloride, you can get a tertiary alcohol.
That wasn't the question, though.
And you could do that, right? This alkylithium could add to an ester, and maybe it would add twice. But it's hard to get it to not add the second one because the ketone is more reactive than the ester. So what did we add it to that produced the ketone instead? A different carboxylic derivative. Or in other words,
Is it like one of the reactive ones?
what's the answer to this question? Yeah. Sorry, not that.
Oh. The aldehyde, or it's aldehyde or anhydride? I can't decide which.
So if we added it to the aldehyde,
Oh, it would give us an alcohol again, wouldn't it?
you get a secondary alcohol out.
Okay.
That's protein, right?
And then we'd have to oxidize it.
And then we could oxidize that up and any oxidation too. So that would be a way of making that and would be correct. But we could do it in a single step. Well, without isolating the ingredient. If you add it to the acid chloride, or the anhydride for that matter, that reaction is not going to stop with the ketone. You're going to make the ketone, because the ketone is going to react with more and makes a tertiary alcohol. So if you're after alcohols, adding to the aldehyde or adding to the acid chloride or adding to the ester with an alkylithium reagent or an alkyl-magnesium bromide is the answer. But if you wanted to stop at the ketone, that's not the answer. And remember, we could get it to stop at the ketone from the acid chloride if instead of using an alkylithium or an alkyl-magnesium bromide, we use the cuprate. But that isn't the cuprate. That's an alkylithium. So what can we add an alkylithium to that will produce ketones, not tertiary alcohols or secondary alcohols? And it's a carboxylic acid derivative, right? So it was in the carboxylic acid capture. Well, we know it's not an acid chloride, and we know it's not an anhydride, and we know it's not an ester. What are the other two carboxylic acid derivatives?
Like one with the nitrogen?
One with the nitrogen. What are those two? Acid chlorides, anhydride esters, amides. That's not the answer. What's the
Well, I
last one?
figured.
Hmm?
I said I figured it was not the answer.
So what's the other nitrogen-containing carboxylic acid derivative?
Nitrile? Wow, why did I guess everything?
So that can add to the corresponding nitrile.
Oh, that makes so much more sense.
This is reagent going to add to nitrile. Generate that salt, and then aqueous acid will hydrolyze that to carbonyl. So now you have a ketone adjacent to your dithiane ring instead of the alcohol. Say mercuric chloride, remove that. Now you've got the dicarbonyl compound where you have two carbonyls adjacent to each other. This ring where you have two carbonyls like that sandwiched between two benzene is a benzyl. This would be 3,5-dimethoxy benzyl. So we can make alpha-diketones by taking our dicyanine anion, and instead of adding it to an aldehyde, we add it to a nitrile. Right? If we want alpha-hydroxy ketones, we add the dicyanine anion to an aldehyde. If we want alpha-diketones, we add it to a nitrile. And in both cases, you have to remove the protecting group using the mercuric chloride. And we have 5 minutes left. I'm not going to use it. Cut out a little early. It said in the syllabus that the other topic for today's lecture, in addition to these alpha dicarbonyl compounds and alpha-hydroxy ketones, would be mass spectrometry. I am planning to talk about mass spectrometry in lab this week with my group B because they need mass spectrometry. I'm not sure if I'll have time during lecture to talk much about mass spectrometry, but there is a little mini lecture on mass spectrometry on last semester's lab. So if you go to Chemistry 260 lab on YouTube, there's a little mass spectrometry lecture that I did for my lab section last semester that you could watch in preparation for covering little mass spec later. The quiz won't have mass spec on it though. The quiz will have diazolium salts and or